Hey guys, Ms. Gosling here. In this video, you're going to learn about charging and discharging capacitors. By the end of the video, you'll be able to describe the behavior of charging and discharging capacitors. So let's go ahead and get started, shall we? So let's go ahead and take a look at the circuit below. And this circuit below is something we call an RC circuit, which is simply defined as any circuit with both a resistor and a capacitor or capacitors. Because of course we can always use our equivalent capacitance to figure things out in our circuit. So an RC circuit will often be constructed like what you can see below, with some sort of a voltage source and a switch that we can move to either open the circuit to the voltage source or to cut the circuit off from the voltage source. So when the switch is moving to that red position, like so, our voltage source is going to send a current through our circuit and is going to charge the capacitor. And when that happens, charges, so, bunch of coulombs, bunch of electrons are going to hang out on that capacitor and are going to be collected up until the capacitor is full. Then, when the capacitor is full, we can take our switch and move it to that closed position so that we're no longer connecting the EMF to our circuit. And in that case, our capacitor is going to discharge. So the charge that has been built up on that capacitor is going to leave and it's going to create a current through our circuit and is going to create a current that travels through our resistor. So that's kind of the basics of an RC circuit. Now, one last important thing that you need to know is that when we are charging our capacitors, when we have that switch in that red position, the current in our circuit is going to decrease over time. And that is a really fundamental part of that RC circuit. So again, when our capacitor is charging, the current in our circuit is going to decrease exponentially. Similarly, when the switch is in our blue position, we're going to initially have a really large current. And that makes sense, of course, because the potential difference across our capacitor is very high. But as the capacitor discharges, the voltage across the capacitor is going to decrease, and as a result, the current in our circuit is going to decrease. So again, when a capacitor is just both discharging and charging, the current is going to be at its highest right when we switch from charging to discharging, and it's going to decrease over time. Now, when our capacitor is discharging, it is going to follow an exponential discharge rule with that characteristic graph of the shape that you can see right here. So if we have charge versus time being measured on that capacitor, that charge is going to decrease exponentially over time. Similarly, we can continue to charge up a capacitor as the capacitor is going to charge until it reaches the maximum charge that it can hold. So you can see that this graph shows a logarithmic shape, and that is exactly what's going to happen. So our capacitor is initially going to charge very, very quickly, and then over time, the amount of charge that is being held on the capacitor, the voltage differential across that capacitor, is going to increase much more slowly until eventually it reaches that steady state period and has its maximum charge. And at that point, that's when we would want to switch our circuit and discharge that capacitor. So the last thing I want to introduce you guys to is something called the time constant. And we define the time constant as the time required to charge the capacitor to 63% of its maximum charge. It is also, coincidentally, well, really not coincidentally, the time required to discharge the capacitor by 37%. Now, I also want to mention that the maximum charge for a capacitor is going to be reached at 5 times that time constant, which we're going to represent with the letter tau. So that's the Greek letter tau, which is the time constant. And we can actually calculate our time constant by just knowing the resistance in our circuit and the capacitance in the circuit. And the equation that relates those two is that the time constant tau is equal to the resistance times the capacitance. So if we've got, and specifically it's the resistance, of course, of the resistor and the capacitance of the capacitor in our circuit. So let's go ahead and take a look at example 1. So in this problem, we have a graph of the voltage versus time for a capacitor, and we have labeled here at this position, at this moment in time, we are at 10 volts. Using this graph, I would like to figure out what the maximum voltage of the capacitor is. So I know that at 1 times my time constant, I am at 10 volts. So at my time constant, my voltage is 10 volts. I also know that by definition, at my time constant, my voltage is equal to 0.63 times my maximum voltage. And that, of course, comes from the definition of our time constant, which is the time that it takes for our capacitor to reach 63% of its maximum capacity, of the maximum voltage it can hold. So that means that 10 volts is equal to 0.63 or 63% of our maximum voltage. Dividing both sides by 0.63, we get that the maximum voltage that our capacitor can have is approximately 16 volts. So that is the maximum voltage that our capacitor can hold. Let's go ahead and take a look at another example. A 10 microfarad capacitor is hooked up to a circuit with a 9-volt battery and a 10 kilo ohm resistor. How long will it take the capacitor to charge to 63% of its maximum? So let's go ahead and go through the guess method for this problem. So our givens are the capacitance of the capacitor. C is equal to 10 times 10 to the negative 6th farads. The voltage of the battery, which is 9 volts. And the resistance of the resistor, which is 10 times 10 to the 3rd ohms. Now I need to find my unknown. And my unknown is a little bit sneaky here. So I know I'm trying to find a time, and I know I want to find the time that it takes the capacitor to charge to 63% of its maximum. So that 63% tells me that my unknown is my time constant tau. Because again, by definition, the time constant is the time that it takes my capacitor to charge to 63% of its maximum voltage. So let's go ahead and write our equation. So I know that tau is equal to my resistance times my capacitance. And that means that I am ready to sub and solve. But before I do that, I'm going to go ahead and just cross off this piece of information about voltage because it's not in my equation and is therefore irrelevant. So substituting and solving, I know that tau is equal to my resistance, so 10 times 10 to the 3rd, times my capacitance, which is 10 times 10 to the negative 6th. And when I solve that out, what I get is that tau is equal to 0.1 seconds. And there you go. I have solved example 2 for you. So let's go and talk takeaways. So first of all, capacitors can both store charge and release it. Capacitors discharge exponentially and charge logarithmically. And the time constant tau is equal to resistance times capacitance, and is the time required to charge the capacitor to 63.2% of its maximum. And there you have it, guys. You now know everything you need to know about capacitors. So go ahead, give our capacitor problems a try. Best of luck and happy solving.